So data representation, on the other hand, is something which lets you store your data inside computer, but there are different ways you can represent your computer, right? So I'm going to give you a quick example for that. Let me. So for example, if I say that I have like 10 apples, right? I can also say, right? So if I want to change this statement, I want to, say that I have a apples, right? So this is also correct, and this one is, obviously correct, right? There's another example that I say that it is, yeah. So you are more familiar with this statement. I guess you guys should be more familiar with this. That I have, you know, X apples. Do you guys know Roman numbering? Yeah. So this is 11, and this is 12, and this is 5, and this is 4, right? I hope you guys remember. This is 6, right? So although we are able to write these things in a simpler way like this, or like this, or like this, or like maybe this, or this. So we can say that all of these are different ways to represent the same number. So if I were to say that I have, sorry, if I were to say that I have 11 apples, I could write 11 like 1 1. I could write in English 11. I could write xi, and it would still be understood by many people that this is 11. And let me show you another way that how the computer people do it. They also call it b. They also call this one c, but they stick to calling this one 5 and this one 4 and this one 6, right? And let me actually even show you another way of writing the same number, the exact same number. There is not going to be any difference in this, and that one would be 1011. And they sometimes write this number as 1100. They sometimes write this number as 0101. Okay, so all of these are, so we call this Roman numbers. Changing the representation and converting a number, there's a difference, slight difference between that. So what I mean by that is, so for example, if I write over here, by the way, I could be slightly wrong, but let please bear with me. These are like rupees, and if I write here dollars, I could write like this, right? So if it was, I don't know the conversion rate right now, but I think it should be somewhere around this, right? So if I write over here 1000, I would write here, sorry, 1600, I would write something like $10, right? So what is going on over here is different from what is going on above in the table above. These are two different things, right? So in the table below over here, this table is actually converting numbers from one, you can say, domain to another domain. While in this table, what is going on is we're simply changing the representation, and the value is not really affected at all. These are absolutely just different ways of calling one number. And let me actually, I know another language, like you can use Urdu, right? You could write, we call it gyara, or we call it bara, right? And these are all representations, right? You're not actually changing the value by any decimal place, no matter how, not even to the 0.000001, not even to that accuracy. You are, changing the value. You're simply changing the representation. These are exact same numbers or values wherever you go in a horizontal row within this, line. But if we convert something, so I call this conversion, and I call this um, changing representation. So what I'm trying to say is that these are different things. Do we need to memorize these? So the thing is that we have become familiar with reading Roman numbers. We are familiar with using English language, and in our case, Urdu language. And we are also familiar in writing in decimal numbers. But this particular format, we are not really, accustomed to, using. These are only used by specialized domain people. Like these numbers are used by CS majors, and they happily communicate values of variables in these number formats, like so their counting starts from 0, goes up to, goes 1 2 3, goes up to, let me actually write all of these, and goes up to 9. And when they finish 9, they continue the counting. Instead of 10 to A, then B, then C, then D, then E, then F. And when they are finished with this pattern, now they reset the pattern to 10. So now their 10 appears somewhere around here. So now their 10 appears. So we're calling this hexadecimal numbers, right? Okay, so these numbers will continue like this. Like, so I think you said 23 maybe. So let's go up to 23. So on the other hand, these numbers, they are unique up to 16 different what I call symbols. These are symbols just to represent a different quantity, right? So 3 represents uh, 3 apples. So I cannot really draw apples over here. So 3 represents 3 apples, whereas this 3 also represents 3 apples. 10 represents 10 apples, whereas A in hexadecimal number format also represents 10 apples, exactly 10 apples, right? Similarly, 16, you all are familiar. When I say 16 burgers, you know that there are 16 burgers, right? But if I say 10 burgers in hexadecimal, you need to understand that I'm talking about 16 burgers and not the usual 10 burgers. So how we differentiate in English language from making this mistake is whenever we are outside the decimal representation in some other representation mechanism, we instead of calling it 10, we call it 10. We only name this one 10 and we don't call this 10, we call this one a 10, just to remain different from the usual decimal representation, right? So then it continues like this, right? So it will continue like this, and let me do this. So now you can see, as someone asked the question, what would 23 look like? So you now know that in hexadecimal 23 apples or 23 cars, they will be called 17 cars. Like we could call it 17, but it wouldn't be really right to do that, because 17 in the decimal is already something that we are familiar with, so we don't call it 17, we call it 17, right? So I will go with 1D, then I will go to 1E, then I will go right. So I hope you see the thing going on over here. I started with 0 1 2 3 4 5 6 7 8 9. So as soon as I thought that my number symbols are finished, and I have to repeat the pattern, I realized that I am in hexadecimal format, and now I need to continue using A, B, C, D, E, F. Right, good. So this is a basket, right? So inside the basket right now, I am assuming that there is nothing that is put inside the basket, right? So we were humans from beginning. So we always had like 5 fingers in one hand and 5 in the other hand, right? Are these 10? Yeah, these are 10, right? So what happened was that we, you know, came up with names for each of these fingers. We called some people, and I know counting in Turkish. So if there is no, nothing in the, basket, they call it sifr. And if there is like one egg in the basket, they will call it beer, right? So they'll call it beer. And if there are two, uh, you know, uh, eggs in the basket, they will call it iki. And at the same time, when humans in the Turkish region, they're developing their counting skills. The humans in our region, they started calling this cipher. They also took this word from Turkish language, cipher. They started calling one as you know ek, right? So if I so they started calling this ek, and they started calling this one do, right? And the list goes on. And at the same time, in the European region, in England, they started calling this as 0, and they started calling this as 1. They started calling this as 2, right? And Sifar, Bir, Iki, Uch, Dord, Besh, Altayade, and so on. And whereas we started calling it ek, do, teen, char, panch. So essentially, what are we doing? And mathematicians all across the world, they started using the same language, which was the number language: 1, 2, 3, 4, representing by the way, writing the numbers in this way: 6 and 7, right? So I hope you guys get the idea. What I'm trying to tell you guys over here is that these are just representations which we had to invent, which was facilitated by the luxury of having 10 fingers. So everywhere in the world you go, you will see at least 10 different names for these 10 first 10 numbers. English repeats the pattern after 10, whereas Turkish also repeats the pattern after 10. They only have different names for 10, 20, 30, 40, 50, 60. While this is something that I really cherish a lot, that Urdu language has 100 different words for 100 different numbers, starting from 1 going up to 100. You can try it. So it was a nightmare as a student when I was young, when we had to remember Urdu counting from 1 to 100. So we were forced to memorize that. And now I see people really don't know counting in Urdu from 1 to 100, but because all the numbers have different names, every single number has a different name. So you could say that, sir, if we were to take your advice, we would say that people in India and Pakistan, they used to have 100 fingers. So of course, that would be wrong. So taking this example a bit further, so there is a person, a guy who looks like a computer, who also has hands, and on each hand he has 8 fingers, right? So this is called a hexadecimal computer, right? So on this hand, this person goes from 0 to 7, and on this he goes from A to F. And let me give you another introduction to another real computer, the real computer guy, this person. This was the real computer, and this computer had 2 hands, of course, but this poor guy only has 2 fingers, one finger over here and one finger over here, right? So when the computers were built, these computers were only given 2 symbols. One was called 0 and the other one was called 1. So you do not see any number above 0 and 1 in computers. So if I go to the same table over here and I tell you that the real computer, name of that computer is called binary. Okay. So I'm going to do something really, really amazing, and I am just going to get the binary sequence out of you guys instead of me telling you what the sequence is. Numbers, you will see that as soon as we were done writing the first 10 symbols, we incremented the left side location to one more number, and we started repeating the pattern on the same location that it had ended before. So here you can see the sequence have started again: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The difference between this group of numbers and this group of numbers is that on the left hand side of these group of numbers, the number has actually gone up, one up as before. And it the same difference as we see in the decimal numbers, that this first group are 16 unique symbols, and the second group is the same unique symbols, but the left hand side number has incremented to one, incremented by one. So this was what hexadecimal was all about. Now coming to binary, I say that when I do this, my first group of numbers is done with, right? So now I need to restart the pattern, but still keep the new pattern different from the previous pattern. How would I do that? But in these examples, what we didn't do was we finish up to 100. So if I were continuing this number and I reached 99, the next number would be what? 100. So first,
Yeah, yeah.
let's see the what's going on over here. We reset both the patterns in the numbers which are on the rightmost side, 9 and 9. We reset both the numbers, and now the pattern will continue for all the 99 numbers in the 100, 101 up to 199 and then 200, right? So the pattern repeats itself. And similarly, if we were going in this number system, hexadecimal, and we reached a point where we had, first of all, we will get numbers like A1, A2, and then they will continue, and we will then get B8 and then B8, then B9, and then there would be BA, and right. So we will continue with B sequence, and we will go up to BF, and then there will be C0, and then that will keep on continuing, and we will reach a point where it will be A, then EB, then no, actually not E, FA, FB, and then it would be FC, and then FD, then FE, and then FF. And what would happen after FF? Because we have exhausted all the symbols in both the number locations, we would do 100. like this 101, 102, and up to 10f, and then we will do 110, and then 111. So probably it has gotten complicated at this point, but before that it was pretty simple, right? So let's come back to the binary numbers. So if you continue over here, you have exhausted both the symbols, the binary symbols over here. So you will reset these symbols, but before you do that, you will write a 1 on the left hand side of the two symbols, right? So this is, so let me just show you how it is done. So then you will increment this, then you will write 1000, and then you will write 1001, and then all these three numbers will be reset only if they reach the value 1. So then it will be 1001, then 1010, then 1011, then 1100, then 1101, and this is how. And the number of digits, they change very quickly in this scheme of representing numbers, right? So, and then there is 1111, and then it would be 10000, 10001, 1010, right? So this is how the number of digits change in binary system. If I ask you a question that convert this 12 into binary number, so if I ask you that convert this number 12, which is right now in decimal format, into binary without looking at this translation table, is there a mathematical way to do that? So the answer to that is that yes, there is a way of doing that. So you write down 12 over here, you draw a table like this, you divide this 12 by 2, right? Like this, 2, 6, or 12, and you write down anything that is remaining after this division, right? So let me actually show you in this traditional way of writing long division. So if this is 12 and this is 2, you write 6 over here or on the right hand side wherever you are used to writing this. So you get 12 over here, and at the bottom you get 0. So this thing we call this thing the remainder, and this is called the quotient q, right? So now let's and then you repeat this process as long as you get a number which is greater than 1. So you divide it on 2 again, and you get 2 3s are 6, and you get 0 as a remainder. By the way, sorry, so I had to write something over here. All of these things, these are the q's. All of these things, this one and this one, and all of these things like this one and this one, these are the remainders. Okay, so now you go to divide it again because this 3 is still greater than 1. So you divide it by 2, and you get 2 ones are 2, and on the remainder side you get 1. Let me show you it. This to you in long division style. So if you're dividing 3 by 2, so you get 2 ones are 2, and 3 minus 2 is 1, right? So this quotient 1 has gone over here, and this remainder 1 has gone over here, right? There is another, so you can stop over here, or you could do another step, and I will be collecting all of these numbers. So I will collect this and this and this and this in such a way that I start from this point, go to this, then I pick this one and I go to this, then I pick this one and I go to this, and then I pick the last one. So I am going to show you how I wrote these numbers by writing over here these numbers. So these numbers are 1 1 0 0. So you can see that this one came over here, this one came over here, this one came over here, this 0, it went over here, this 0 also went over here. So now you know that you started with a number that we call 12, and we landed on a number that also represents 12, the quantity 12, but we are writing it as 1100 because why? Because it is in this number format. It is in the format of a computer which has only two fingers. One finger is called 0, the other one is called 1, and here you can see that this quantity 1100, it doesn't have anything other than 0 and 1, only zeros and ones, right? And to officially write this number, what we do is we place square brackets on the left and right hand sides of this number, and we write a tiny 2 at the bottom right of this number to represent that this number is in binary format. Any questions? Okay, so if you want to do it quickly, you can go to the calculator and you can go to the scientific version, and you could write 23, and you could sorry, not scientific, the programmer view. So you could write 23 and go to the see the binary representation, which is 10111.